In this video, we continue with chapter 4.4 examples, and we will be looking at linear dependence and linear independence. Our learning objectives for this video are to determine whether a set of vectors in a vector space V is linearly independent, and to prove results about spanning sets and linear independence. So sometimes one vector can be written in terms of other vectors. So for example, back in earlier examples, we saw S2, which were vectors in the plane, but not vectors that span R3. And with these vectors S2, we can actually take vector 3, 2, 4 and write that as a linear combination of the other two vectors. So we could calculate out that vector 3, 2, 4 is just vector 5, 7, 6 plus vector 1, 3, 2 added up and then divided by 2. So we would say that this vector 3, 2, 4 is dependent upon the other two vectors 5, 7, 6 and 1, 3, 2. 1, negative 3, 2. But just as easily, we could solve for 5, 7, 6 in terms of the other two vectors. So there's no good reason to single out this vector 3, 2, 4 as special when any of the other vectors in this set could be written as combinations of the other two. So a more equitable equation is to say 1 times 5, 7, 6 minus 2 times 3, 2, 4 plus 1 times 1, negative 3, 2 is the 0 vector, 0, 0, 0. So in this case, C1 equals 1, C2 equals negative 2, and C3 equals 1. But those aren't the only values that would work here to give us 0. In fact, any multiples of these values of C1, C2, and C3 are still going to cancel out these vectors and give us zeros as a result. So imagine if we multiplied through by the constant 5, then C1 would be 5, C2 would be negative 10, and C3 would be 5. So we say, in fact, there are an infinite number of solutions here to this equation C1 times 5, 7, 6 plus C2 times 3, 2, 4 vector plus C3 times 1, negative 3, 2 vector equaling 0. So we write this in terms of free parameters here. We say C1 equals T, and then C2 is going to be negative 2T, and C3 equals T. T can be whatever value you want, and then you can always find these coefficients that will solve the equation equal to 0, including when the coefficients are 0. So if we let T be 0, then we get C1 equals C2 equals C3 equals 0. All right, on the other hand, remember our set S1 that did span R3? So S1 was almost the same as S2, except we had a 4 as the first value in that second vector. So the only solution to the equation C1 times 5, 7, 6 plus C2 times vector 4, 2, 4 plus C3 times vector 1, negative 3, 2 is going to be 0, 0, 0, the 0 vector. Or if we want to write it in terms of matrices, our coefficient matrix times C1, C2, C3 equals 0 only if the values C1, C2, and C3 are all zeros. So this is known as the trivial solution, and you could work backwards if you wanted to do that multiplication and verify the inverse of the coefficient matrix times the 0 vector is only going to give us zeros there. So when the only solution to a system like this is a trivial one, where the coefficients or scalars are 0, the set S is known as linearly independent. You can't write the other vectors as combinations of each other. When a non-trivial solution exists, in other words, you get non-zero values for the scalars, the set is linearly dependent. That means you could write some of the vectors or all the vectors as linear combinations of the other vectors. So here's our definition of linearly independent. If S equals vectors V1 through Vk, a set of vectors in the vector space V, then S is called linearly independent if and only if this equation C1 plus V1, where the C's are scalars, plus C2 times vector V2 all the way through adding CK times vector VK equals 0. If that equation has only the trivial solution where all the scalars are 0, then our set S is called linearly independent. Our set S is called linearly dependent if and only if there are also non-trivial solutions. So we are going to work out 4 examples here using these given vectors. W1 is going to be 7, 3, 5, or 7, 3, negative 5. W2 is going to be 1, 4, 6. W3 is going to be 9, 11, 7. W4 is 12, negative 5, negative 4. And W5 is negative 6, 5, and 8. So let's take a look at example 1. We're going to ask 2 questions here. Is the set W1, W2 linearly independent? And does the set W1, W2 span R3? So we have 2 things to determine here. So to determine linearly independence, we need to solve this equation C1 times W1 plus C2 times W2 equals 0. And then to decide if it spans R3, we need to solve C1 W1 plus C2 W2 equals an arbitrary vector V1, V2, V3 for an arbitrary vector in R3. So both equations are the same on the left side, and then on the right side in the check for linear independence, we check the 0 vector over there, and the check for spanning, we check the arbitrary vector V1, V2, V3. Okay, so rearranging, if we multiply our scalars C1 and C2 through, we have 7C1, 3C1, and negative 5C1, plus 1C2, 4C2, and 6C2, and we're setting that equal to arbitrary vector V1, V2, V3. So then I'm going to combine the first elements together. I'll combine the second elements together and the third elements together here to get this equation or set up here with the vectors, where 7C1 plus 1C2 in the first element, 3C1 plus 4C2 in the second element, and negative 5C1 plus 6C2 in the second element are all equal to elements V1, V2, V3. So if we set that up with these arbitrary elements, V1, V2, V3, we see the values from the first element, the 7 and 1. So in the top row of our coefficient matrix, the values 3 and 4 from the second element go into the second row of our coefficient matrix. And the values negative 5 and 6 from the third element go into the third row of our coefficient matrix. You can see if you multiply those by C1 and C2 as a column vector, you just get back out this same equation that we had up here equal to V1, V2, V3. So we're just translating our vectors to matrices. Remember, we can translate vectors to column matrices or row matrices. In this case, we're translating them to column matrices. So our coefficient matrix here is not square. So right away I can see it looks like there's some issue there in terms of spanning. So we can't do a determinant. So instead we do the reduced row echelon form. So you would do this by hand with equations. I've already worked it out for us over here. So to get ones here on the diagonal, we end up with this system here rearranged in terms of V1, V2, and V3. And notice in the bottom row here, we get zeros. This wouldn't work well typed in a calculator or Mathematica because they would treat those variables differently and have a hard time working with this. So just beware if you put something in with 2 unknowns into a matrix calculation, you might end up with zeros instead of a rearrangement like this. Okay, so here's our system over here. And so let's look at how this could solve. So if we are thinking about our first question here, is W1, W2 the set linearly independent, we can set V1, V2, V3 equal to 0. So in that case, if these are all zeros, we only get this trivial solution, C1 is 0 and C2 is 0. You can think about each variable Ci as corresponding to a pivot, where the number of pivots is n. So because this is C1 and C2, we've got 2 pivots. So you can say, okay, therefore W1 and W2 is linearly independent. On the other hand, if there are many choices of V1, V2, and V3, if they're not 0, for this last equation, here 0 equals V1 minus 47 V2 over 38 plus 25 V3 over 38, then there are many choices that could solve that. So this is going to happen whenever our reduced row echelon form has a row of all zeros, like we got over here in the bottom row with the 0, 0 there. So in that case, if you think about it in terms of dimensions, W1 and W2 don't span R3. They're stuck in a plane together. So notice that to answer these questions, we didn't need to pay attention to the coefficients on the right-hand side of the line in the augmented matrix. All that we needed to know was the coefficient matrix on the left-hand side over here. So we are just working with our coefficient matrix. Example 2 asks us to consider, is W1, W2, W3 as a set linearly independent, and does W1, W2, W3 as a set span R3? So to decide the linear independence, we want to solve this equation C1 times W1 plus C2 times W2 plus C3 times W3 equals 0. And to decide spanning R3, we are going to solve this equation equal to an arbitrary vector that I'll call V here. So you can just say V in vectors 1. So using block multiplication that we saw back in chapter 2, we can just say, okay, W1 here, W2, and W3 as blocks in that coefficient matrix times C1, C2, C3 equals V1, V2, V3, or if we put in our values here for W1, W2, and W3, we see they each correspond to a column because we're translating our vectors to columns here. And so this is not invertible because if you go check in SIMPy, its determinant is 0. So you're welcome to pause the video and go check and verify that. So this tells us that sometimes we cannot solve C1 V1 plus C2 V2, C2 W2 plus C3 W3 equals our vector. So it does not span, this set does not span R3. It also has an infinite number of solutions, so the set is linearly dependent. So our answers for example 2 here would be no, it's not a linear independent set, and no, the set does not span R3. Here's another way you could think about it. If you take our coefficient matrix and put it in reduced row echelon form, notice you get zeros down there on the bottom. We'd say the third column in the matrix doesn't have a pivot. We're getting a free parameter down here. So we'd say, okay, we're gonna let C3 equal T, that free parameter. And then the solutions are dependent. If C3 is T, then C2 is negative 2T, and C1 is negative T. So since we have non-trivial solutions, whatever T is, you can get solutions for the other values and get zeros out. Then we say these sets of vectors, W1, W2, W3, the set is linearly dependent. To investigate spanning, we would set the right-hand side equal to the arbitrary numbers. The third row of all zeros in the matrix is going to give us 0 C1 plus 0 C2 plus 0 C3 equals some sort of number, which has no solution if the right-hand side is not 0. So we have this problem of what we think of as fewer pivots than we have equations. You can think about that we have 2 pivots, but 3 equations. So therefore, we get to conclude that this set W1, W2, W3 does not span R3. Okay, let's take a look at example 3. Example 3 asks, is W1, W2, W4 as a set linearly independent? And does W1, W2, W4 span R3? So again, to decide linear independence, we're going to solve this equation with our coefficients C1, W1 plus C2, W2 plus C4, W4 equals 0. And to decide spanning, we're going to set the equation equal to an arbitrary vector V. So again, using block multiplication, we'll say W1, W2, W4 as the blocks or the columns, because we're representing the vectors as column matrices in this coefficient matrix times C1, C2, C4 equals V1, V2, V3 is an arbitrary vector. So as we carry out these calculations, we see our coefficient matrix here is invertible, also known as non-singular, because its determinant, if you go check in SIMPy, is 591. So this tells us that we can solve this equation here, C1W1 plus C2W2 plus C4W4 equals V. So we can say the set W1, W2, W4 stand bar. This also tells us that if we set our equation equal to 0, there's a unique solution. So the set W1, W2, W4 is also linearly independent. And here's our 3D drawing over here, and you can see, hopefully, that the values are not in the same plane, and they do span R3. So for example 4, we're going to check the set W1, W2, W4, W5 to see if it's linearly independent and does it span R3. So notice before we had 3 vectors that we were checking for linear independence and spanning, and now we're checking a set of 4 vectors. So to decide linear independence, we're going to solve this equation, C1W1 plus C2W2 plus C4W4 plus C5W5 equals 0. And to decide spanning, we're going to set this same equation equal to Z, an arbitrary vector. So we can use block multiplication and rewrite as W1, W2, W4, W5, or we can replace those columns with the vector values. And we are going to get this coefficient matrix multiplied by the column matrix C1, C2, C4, C5, corresponding with the scalars. And we're going to see, does this equal arbitrary vector V1, V2, V3? So notice our dimensions are 4 dimensions for our 4x4 matrix and our 4 scalars. And we're trying to see, does this equal a arbitrary 3-dimensional vector? So it's a non-square matrix, so we can't take the determinant, so we go to the reduced row echelon form. And so we see the 4th column over here in the matrix gives us a free parameter down here. So because we don't have that 4th value, so there's a linear dependence relationship here. And it makes some sense because we had 4 dimensions that we were trying to map to 3 dimensions, so you're going to get dependence in there. And then to investigate spanning, we see that there is no row of all zeros here. Every row has a pivot, so we'll never have an inconsistent equation where 0 equals some sort of number. So we can say that this set does span R3. So you can have a linearly independent or linearly dependent set that still spans R3. So the steps we've been using to test for linear independence and linear dependence can be summarized as 3 steps. So the first set is from this vector equation, C1, V1 plus C2, V2, all the way through adding CK, VK equal to 0. You write a system of linear equations in terms of the variables, C1, C2 through CK. Then you determine whether the system has a unique solution. And you can do that using the determinant or reduced row echelon form. And then if the system has only the trivial solution, where all the scalars are 0, then we say the set is linearly independent. If the system has a non-trivial solution, then the set is linear dependent. Okay, in the next example, we're going to look at some theorems. So we will do that in a continuation video.